Hello and welcome back for another exciting presentation. This time we're going to talk about the all famous Lewis structures, how to construct them. See it in part of Unit 2. Unit 3 will be the next one. I'll start with the intermolecular forces, which is a big topic and almost certainly will be on the exam. Lewis structure is a lot packed into a little bit on Unit 2, so this has got its own little doohickey, I guess. Here we go. Lewis structures. If you follow the rules, you're going to get it right most of the time. First off, you sum the number of valence electrons. In this case, Cl's got 7. 7 times 4 is 28, plus carbon, which has 4, which would be 32. Connect all atoms to the central atom. Remember, when writing the formula, the central atom is listed first most of the time, except for hydrogen, which, if it's listed first, you skip that one and go to the next one. All right, I should connect all atoms to the central atom with a single bond. So here we have the line of a single bond, so there's 4 single bonds to carbon. Complete all octets of the non-central atoms. So now you would go through and you'd add 6 electron pairs to each of the atoms connected to the central atom. Place any remaining electrons in the central atom. I've got 4 each with 8. 8 times 4 is 32. My original number was 32, so I have 0 extra. Check the central atom for an octet, and I've got 2, 4, 6, 8 on carbon, and that's how you do it. This is done. Now, again, this is more difficult with the completed one to kind of go through the steps, but you look at this one, which we see already has a double bond. You're going to sum the valence electrons. 7 is 14, plus 6 for oxygen is 20, plus carbon is 24. You would connect these with a single bond and distribute the octets. After doing so, you'd have 24 valence electrons used. You'd have 0 left over. If at this point you wouldn't have this extra double bond here. So when you check, you'd see there were 6 from carbon. And then you would make a double bond. You would take an electron pair that you'd already used to complete an octet, and then bring it down and make the line, make it a double or triple bond. You may wonder, well, why didn't I use chlorine? Why didn't I double bond chlorine here? Why is it oxygen? You could have picked it. You would be wrong, but you could have picked it. And how you determine that is through a concept called formal charge. Formal charge. We did earlier in the year. You take the number of valence electrons and you subtract it from really the number of electrons that are used in the bond. All right, the number of bonds and the number of unshared pairs of electrons. Add that up, subtract it from the number of valence electrons. For instance, I've got sulfur here. Sulfur has 6 valence electrons. And here I've got 1, 2, 3 single bonds. So that's the number of bonds. I have 3 bonds. So it's a triple bond. 3. 1, 2, 3. It's poorly. I don't like how they did this one. It's the best one I could find. And then here is the unshared pair of electrons, and that counts as 1 and 2. So you have 3 bonds, 2 unshared pairs of electrons. That's 5. 6 is the number of valence electrons. Minus 5 is plus 1. And you look at carbon, it's got 3 bonds, 1, 2, 3, 4. 4 valence electrons, 4 minus 4 is 0. And the nitrogen, 1 bond, right? It's 1 bond. And then 1, 2, 3, 4, 5, 6 valence electrons that are not bound to the bond would be 7. And then the valence electron here is 5, so 5 minus 7 is minus 2. So in checking your structures and trying to pick out which one's the best and whether or not I have a double or triple bond, you want to closer to 0 the better. So obviously this one is got a minus 2 and a plus 1. This one's got 2 zeros. And you want the more electronegative atom to be negative formal charge. And if you remember your trend, that's helpful. Nitrogen's more electronegative here, so you want it to be negative. And again, this one's more preferred because it's closer to 0. If I go back to this structure, if you were to put a double bond in chlorine, all right, that would kind of mess up the formal charges here. You'd have currently, I think they're all at 0, 2, 4, 6, 7, and that's 7, so 7 minus 7 is 0. 1, 2, 3, 4, 5, 6. Oxygen's at 6, so that's going to be 0. Carbon's at 4. At 4, that's at 0. And this again has to be 0. If you had a double bond here, this chlorine becomes, we would have 2, 4, 5. Sorry, I lost myself. If you have the double bond here, right, you eliminate these two. So you'd have 1, 2, 3, 4, 5, 6, and then you'd have 7 minus 6 is plus 1. So that become plus 1. I think this would be minus 1, and this would be 0. Whereas as it's drawn here, with these formal charges are all 0. That's formal charge, just in case you have extra structures. All right, now geometry. You can memorize this earlier in the year. Good recap, good review here. And what you're doing is you're counting. If you look at these, that's linear. If you look at these structures, you're counting. You're looking at the central atom. And here I've got 3 attachments with no electron pairs. And here I've got 4 attachments, no electron pairs. You've got your tetrahedral. And then remember, the unshared pairs of electrons are going to interact. They're closer to the central atom, so they're going to tend to push away the bonded atoms, causing these different structures. You should also know the angles. You got 180, 120, 109.5, as well as this also relates to polarity. Right, some will cancel out. So the linear atoms, any linear structure is going to cancel. If they are the same atom connected to the non-central, all the non-central atoms are the same, it could cancel, in which case it would be nonpolar. Carbon dioxide is an example here. So there's a few shapes that are going to lead to polarity. I think we already had a question related to that. It's a good review. Like this is all 90 degrees. This is, we've got the nice linear 180 structure. It's going to cancel. So there's a number of structures that would cancel, but so you should know the shapes. Again, there's a question I think that would be easy to look up online if they asked it for you. So if they do ask you Lewis structure, it's probably going to be more complicated, carbon-based one, but even then you can probably find it. So it's unlikely that they give you something like that, is my guess, but we're going to look at it anyway. So here are your bond angle extraordinaires. Anything that is going, that will cancel. The 90s are all canceling here. They're all the same. So those vectors cancel. Whew, have a lot of technical difficulties today. So one other concept. So I can't even do it. I don't know what's going on here with this machine. So you get the bond angles, you have the drawing, and now there's resonance as well. When you have a situation where you have 3 identical atoms and you have one, they're not all with double bonds. This double bond can rotate around that central atom, and you end up with this kind of hybrid. And if you look at the double bond here, the length will not be as long as a single bond and not as short as a typical double bond. It'll be some sort of hybrid in between, and really the data would be some kind of hybrid between a single double bond for all 3 of these atoms. So be aware you can find resonance structures out there. And then finally, there's hybridization. It's kind of a nice little summary. Found this on the web. I don't know what number 6 here is, but so you have sp3. If you have 4 atoms connected to the carbon, 109.5. Single sigma bonds, remember, are those single bonds. They're all single. You have 3 connected to the central carbon, no unshared pairs of electrons. I think it's the catch there. sp2, 120. 1 pi bond, 3 sigma bonds. That's 2 single, 1 double. Then you have 2. You have sp hybridization, 180 linear, 2 pi, 2 sigma. Final thought on that hybridization. Remember with the orbitals and how they the s gets energy, the p orbital lowers a little bit of energy, and they become those hybrid orbitals. All right. Good luck. See you next time, I suppose.